Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover trigonometry. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with solving any triangle. The right triangle methods from earlier work only when one angle is exactly 90 degrees. For everything else, surveying with no right angle in sight, navigation across oblique paths, the triangulation astronomers use to measure the sky, you need two more general tools. They are the law of sines and the law of cosines, and between them they solve every triangle. The law of sines. In any triangle, right-angled or not, let A, B, and C be the three side lengths, and capital A, B, and C the angles opposite them. Each side and the sine of its opposite angle are bound together by a single, remarkable ratio. Equation 28, the law of sines. Side A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C, and all three equal 2 times r, where r is the circumradius, the radius of the circle that passes through all three vertices of the triangle. That shared ratio is not just any number. It is the diameter of the circle through all three vertices, the circumscribed circle. Figure 29. A triangle inscribed in its circumscribed circle, with vertices A, B, and C on a circle of radius r, and sides A, B, and C opposite their angles. Each ratio of a side to the sine of its opposite angle measures the same length, the diameter 2r. Animation 13. A triangle is inscribed in a fixed circle, and one vertex slides around the rim while the side-to-sine ratio is read out live. Each side and its opposite angle change as the triangle flexes, yet the ratio between them never moves off the diameter 2r. The law of sines is the right tool when you know an angle together with the side opposite it. The cases angle-side angle, angle-angle side, and the trickier side-side angle. Worked example, triangulation from a baseline. Two observers stand 200 meters apart on a beach, both sighting a buoy at sea. The first observer measures an angle of 75 degrees from the baseline to the buoy. The second measures 60 degrees. How far is the buoy from each observer? Set the baseline as side C, opposite the buoy angle C. The measured angles sit at the two observers, A and B. The three angles of a triangle sum to 180 degrees, so solve for the buoy angle. C equals 180 degrees minus 75 degrees minus 60 degrees, which is 45 degrees. The baseline of 200 meters lies opposite this 45-degree angle, so apply the law of sines. Side A over the sine of 75 degrees equals side B over the sine of 60 degrees equals 200 over the sine of 45 degrees. Evaluate the common ratio from the known pair. 200 over the sine of 45 degrees equals 200 over the square root of 2 over 2, which is 200 times the square root of 2, approximately 282.84. Multiply by the sine of 75 degrees to find side A, the distance from the second observer to the buoy. Side A equals 282.84 times the sine of 75 degrees, approximately 273.2 meters. Multiply by the sine of 60 degrees to find side B, the distance from the first observer to the buoy. Side B equals 282.84 times the sine of 60 degrees, approximately 244.9 meters. The buoy is about 244.9 meters from the first observer and 273.2 meters from the second. The law of cosines. When you know two sides and the angle between them, the case side angle side, or all three sides, side side side, no angle has a known opposite side, and the law of sines stalls. The law of cosines fills the gap. Equation 29, the law of cosines. Side c squared equals a squared plus b squared minus 2ab times the cosine of c. This is the Pythagorean theorem with a correction term. When c equals 90 degrees, the cosine of c is 0, and it collapses to c squared equals a squared plus b squared. Animation 14. Two sides of fixed length are hinged at angle c, which opens from acute through a right angle to obtuse. At exactly 90 degrees, the correction term vanishes, and the law of cosines becomes the Pythagorean theorem. Open the angle wider, and the correction term turns positive, stretching the opposite side beyond what Pythagoras allows. Figure 30. A triangle with sides A, B, and C, and the included angle C, showing how c squared compares with a squared plus b squared as c changes. When c is acute, c squared falls short of a squared plus b squared. When c is obtuse, c squared overshoots it. Worked example, ships at sea. Two ships leave port at the same moment. Ship A travels on a bearing of 050 degrees at 30 kilometers per hour. Ship B travels on a bearing of 110 degrees at 50 kilometers per hour. How far apart are the ships after 1 hour? The angle between the two bearings is the angle C at the port. C equals 110 degrees minus 50 degrees, which is 60 degrees. After 1 hour, each ship's distance from port is a side of the triangle. A equals 30 kilometers and B equals 50 kilometers. Apply the law of cosines to find C, the distance between the ships. C squared equals 30 squared plus 50 squared, minus 2 times 30 times 50 times the cosine of 60 degrees. Substitute the cosine of 60 degrees equals 1/2 and simplify. C squared equals 900 plus 2,500 minus 3,000 times 1/2, which is 1,900. Take the square root to recover the distance. C equals the square root of 1,900, approximately 43.6 kilometers. The ships are about 43.6 kilometers apart after 1 hour. Try it. Find the largest angle. A triangular plot of land has sides of length 80 meters, 110 meters, and 140 meters. Find the largest angle of the plot. Hint: the largest angle sits opposite the longest side. Rearrange the law of cosines to solve for the cosine of C, then take the arccosine. Pause the video now and give it a try. The ambiguous case side-side angle. When you know two sides and an angle that is not between them, case side-side angle, the data may give 0, 1, or 2 valid triangles. This is the ambiguous case, the one configuration where trigonometric data can fail to pin the triangle down. Animation 15. Angle A and side B are fixed, anchoring one vertex. The third side A swings from the far end, like a hinged door. Its free tip sweeps an arc that may miss the base ray, graze it once, or cut across it twice. 0, 1, or 2 triangles from the very same data. Figure 31. The 4 subcases of side-side angle, with the arc of radius A swung from the far vertex against the base ray. The deciding quantity is the altitude h equals b times the sine of A. Comparing A against h and b settles how many triangles exist. Given angle A and sides A and B, compute the auxiliary height h equals b times the sine of A, then compare. The side-side angle subcase rules. First, if A is less than h, no triangle exists. Second, if A equals h, there is exactly one triangle, right-angled opposite B. Third, if A lies between h and B, two distinct triangles exist. And finally, if A is greater than or equal to B, exactly one triangle exists. Worked example, two valid triangles. Solve the triangle with A equals 8, B equals 10, and A equals 30 degrees, finding all possibilities. First test for ambiguity with the auxiliary height h equals b times the sine of A. H equals 10 times the sine of 30 degrees, which is 10 times 1/2, equal to 5. Since 5 is less than 8, which is less than 10, that is, h is less than A, which is less than B, two triangles exist. Apply the law of sines to find angle B. 8 over the sine of 30 degrees equals 10 over the sine of B. Solving for the sine of B gives 10 times the sine of 30 degrees over 8, which is 0.625. The equation sine of B equals 0.625 has two solutions in a triangle, one acute, one obtuse. B sub 1 equals the arcsine of 0.625, approximately 38.7 degrees. B sub 2 equals 180 degrees minus 38.7 degrees, approximately 141.3 degrees. Take the first branch. With B sub 1 about 38.7 degrees, angle C is what remains of 180 degrees. C sub 1 equals 180 minus 30 minus 38.7, which is 111.3 degrees. Then C sub 1 equals 8 times the sine of 111.3 degrees over the sine of 30 degrees, about 14.9. Now the second branch. With B sub 2 about 141.3 degrees, a much smaller angle C remains. C sub 2 equals 180 minus 30 minus 141.3, which is 8.7 degrees. Then C sub 2 equals 8 times the sine of 8.7 degrees over the sine of 30 degrees, about 2.4. Both triangles satisfy the data, one with angles 30, 38.7, and 111.3 degrees and CI about 14.9. The other with angles 30, 141.3, and 8.7 degrees and CI about 2.4. Area formulas. Two area formulas round out the toolkit for solving any triangle. When you know two sides and the angle between them, the area follows at once. Equation 30. The area equals 1/2 times A times B times the sine of C. It is the law of sines' close cousin. B times the sine of C is the height from one vertex, and the area is half the base times that height. When you know all three sides but no angles, Heron's formula gives the area directly. Let S equal A plus B plus C, all over 2, the semiperimeter, half the way around the triangle. Equation 31, Heron's formula. The area equals the square root of S times S minus A times S minus B times S minus C. It is attributed to Heron of Alexandria around 60 CE, though Archimedes may have known it earlier. Worked example, Heron's formula in action. Find the area of a triangle with sides 7, 8, and 9. Compute the semiperimeter. S equals 7 plus 8 plus 9 over 2, which is 12. Substitute into Heron's formula. Area equals the square root of 12 times 12 minus 7 times 12 minus 8 times 12 minus 9, which is the square root of 12 times 5 times 4 times 3. Multiply and simplify the radical. This equals the square root of 720, which is 12 times the square root of 5, approximately 26.83. The area is exactly 12 times the square root of 5, approximately 26.83 square units. Try it. 2 area methods. A triangle has sides of length 5 centimeters and 12 centimeters with an included angle of 80 degrees. Find its area with the 1/2 AB sine C formula. Then use the law of cosines to find the third side, apply Heron's formula, and confirm the 2 areas agree. Pause the video now and give it a try. That wraps up solving any triangle. Next up, Section 9, Trigonometry, P and E, a deep unity. If you found this helpful, like and subscribe and support the channel.